Mi sa che sono ancora in pausa pranzo, Dattolo.
Sono 27.
Ah, ok. No.
27, 28.
Quindi noi non li vediamo.
Esatto, tra poco le do la parola. Ok. We can start. The Professor Cascini is the chairman of this section. Please, Professor Cascini.
Thank you, Dr. Dattola. Ladies and gentlemen, dear friends, good afternoon to everybody. It is really a pleasure for me to be the chairman of this session that is devoted to landslide triggers. During this session, we have 3 presentations. Each of these presentations is 15 minutes long. The first 2 presentations are devoted to the role played by pore water pressure in slope stability. And the third one focuses on the possibility of modeling the groundwater regime in complex geological situation. The first 2 presentations will be delivered respectively by Dilernia, coming from Politecnico di Bari, and the title of the presentation is Assessing the Influence of Hydraulic Boundary Conditions on Clay Slopes Condition. The second one is delivered by Paolo Tommasi, coming from CNR IGAG from Rome, and he asked a question to all of us. Can we correctly model the pore water pressure regime in mudstone and in flysch deposit? Of course, we are waiting for his answer. And the third one is delivered by De Rosa. And De Rosa will focus coming from University of Basilicata. And the title of presentation is Processes and Mechanisms Governing the Transition of Slides into intectonized clay shales into rapid earth flow. The discussion at the end of the 3 presentation will be in charge of Professor Marinos, who is professor at the National Technical University of Athens. Thank you very much for your attention, and please, Dattala.
Now the Professor Dilernia, we can start.
Okay, can you hear me?
Yeah.
Okay, perfect. Good afternoon. In this presentation, I'm going to show a numerical study performed to assess the influence of hydraulic boundary conditions on the instability mechanism affecting a slope in the Italian southeastern Apennines. It is well known that the equilibrium conditions of a slope may be affected by interaction of the soils with the atmosphere, causing the variation of the pore water pressure with time, in turn affecting the stability of the slope, especially where the hydraulic regime is a predisposing factor. Moreover, the impact of climatic variables on the landslide activity depends also on the hydrogeological features of the slope, which control the average piezometric regime. This is particularly the case of slopes made of fine soils bearing a rocky aquifer, where the response to climate of the groundwater in the aquifer adds to the other factors responsible for fluctuations of the piezometric levels in the fine soils. Recent studies highlighted the role played by climatic factors on the landslide activity of clay slopes, location of deep landslides. This is particularly the case of slopes located in the Italian southeastern Apennines, where the activity of several deep landslides was found to be connected to weather conditions. This connection between slope movements and the weather condition has been observed through in situ monitoring data. For example, in this figure, it is shown for the case study of Pisciolo landslide, the variation with time of the 180-day cumulative rainfall, together with the piezometric level measured by piezometers at different depths, and the displacement rate evaluated at the depth of strain localization. It might be observed that the piezometric level varies with time, exhibiting maximum values at the end of winter, early spring, and the minimum values at the end of summer, concurrently with the displacement rates fluctuation. These excursions match a seasonal trend according to the 180-day cumulative rainfall. The same trend might be recognized also for the Pianello landslide located in Bovino, as well as in many other slopes in the Italian southeastern Apennines. So, in these areas, the piezometric regime appears to be a landslide predisposing factor, while the seasonal variation of the piezometric head due to climatic actions represented the triggering factor. A similar scenario applies to the western side of Volturino, which is considered representative of many other landslide cases occurring in the southeastern Apennines. This is
some problems with the audio.
The outcropping clayey portion of phytoflesh, and again with the calcareous portion of phytoflesh. And the calcareous portion, the Fontana Monte Spring is located, giving the name to the western slope of Volturino. So the Fontana Monte slope is affected by very slow-moving deep-seated landslide with the toe in the Giardino stream and mainly developing in the Topo Capuana clay layer. Within the longitudinal section, crossing the landslide body along the maximum slope gradient and extending further beyond the Giardino stream, the outcropping Topo Capuana clay layer overlays the calcareous portion of phytoflesh, which outcrops upslopes, and is underlain by the clayey portion of phytoflesh. Under this clayey portion of phytoflesh, the red flesh occurs, which overlays the sub-Apennine blue clays. The landslide activity of the slope is monitored by inclinometers and piezometers installed along boreholes located upslope and in the middle portion of the analysis of inclinometric monitoring data revealed the presence of a deep sliding surface at about 45-50 meter depth with the toe in the Giardino stream. Along both piezometric verticals located upslope, high piezometric levels are measured. In particular, both piezometers installed along the borehole SC1 measured almost the same piezometric level. This graph shows all the monitoring data. It is shown the variation with time of the 180-day cumulative rainfall, together the piezometric level in red, blue, and green full symbols, and the displacement rate in red, blue, and black empty symbol. It might be observed that, although the monitoring data are not continuous with time, there is a connection between the seasonal variation of the 180-day cumulative rainfall and the piezometric head excursion, with maximum values at the end of winter, early spring, and minimum values at the end of summer. And this is concurrent with the displacement rate oscillation. As previously recalled, at both depths along the SC1 borehole, the piezometric level fluctuations are almost the same, varying between 2 meters below ground level in wet season and 4 meters below ground level in summer. So, in order to identify the source of high piezometric heads at large depth and to investigate the impact of climatic and hydrogeological factors on the slope stability, two-dimensional uncoupled hydraulic analysis of the slope vegetation atmosphere interaction have been performed and associated to limit equilibrium analysis. This is the finite element model implemented for the seepage analysis, accounting for the soil stratigraphy of the geological section. A layer of fractured clay has been implemented along the wall slope profile, overlaying the TPC clay layer. The saturated permeability of the slope soils have been determined through both laboratory and in situ tests, while for the fractured clay, a parametric analysis has been performed to determine the suitable saturated permeability, allowing to capture the hydraulic response in the slope. The partially saturated behavior of the soil has been taken into account through the water retention curves implemented according to the Van Genuchten model. Walls fitting parameters have been calibrated based on the available literature data, selected as to be representative of the retentive properties of the slope soils. The hydraulic boundary conditions have been set to account for the hydrogeological setup of the hill slope, and in particular to account for the presence of the Fontana Monte Spring upslope and of the Giardino stream downslope. So, given the outcropping calcareous layer upslope, representing a hydraulic recharge area for the slope itself, the upstream hydraulic boundary condition has been set to be hydrostatic with water table at 4 meters below the ground level, while the downstream boundary has been set to be hydrostatic with water table coincided with the ground surface. The presence of the Giardino stream imposed to set 0 pore water pressure in this point, while impervious boundary condition has been assumed at the bottom of the model. Then at the top boundary along the sloping surface, free drainage has been imposed in order to estimate the initial pore water pressure distribution. Seepage analysis have been performed imposing a climatic condition to the top boundary, consisting in determining the net rainfall as a function of total daily rainfall and evapotranspiration flux, determined with reference to a representative thermopluviometric year. Then the net rainfall has been cyclically applied for 12 years. This is the result of the steady-state seepage analysis represented in terms of equipotential lines and flow velocity vectors. It can be observed that the seepage rates are much higher within the more permeable calcareous layer fed in the upstream recharge area than in the TPC layer, which is a location of high piezometric heads. So the calcareous layer represents deep aquifer for the slope located below the much less permeable clay layer, and it is the source of high piezometric heads. Here below, it is represented the pore water pressure profile predicted along the SC3 and SC1 boreholes and compared to the average in situ monitoring data. This comparison confirms that the numerical model is capable of simulating the high piezometric level measured even at large depth. Two transient seepage analyses have been performed adopting 2 different values for the saturated permeability of the fractured clay, 1 order and 2 order higher than the saturated permeability of the Topo Capuana clay layer. The numerical results are reported here in terms of variation with time of the pressure head predicted at 25.5 meters and 49 meters along the SC1 borehole. When a higher value of the permeability is adopted, the pressure head rapidly increases at the end of summer and reaching its maximum value and oscillating around it until the beginning of the next summer, when it reduces to the minimum. This behavior is likely to be due to a rapid water infiltration process not counteracted by the evapotranspiration fluxes, which promotes the storage of water in the slope. This behavior tends to be mitigated when less permeable topsoil is considered, for which a better fitting with the monitoring data is achieved at least at the shallower depth. In fact, the piezometric head excursion predicted in the deeper level does not capture the in-situ measurements. So the source of high piezometric oscillation at large depth should be sought in other boundary conditions. For this reason, the seasonal recharge of the calcareous aquifer is taken into account through the simulation of the variation of the groundwater level with time, varying between 3.5 meters and 5 meters depth below the ground level, according to this sinusoidal equation. In this case, the variation with time of the groundwater head only slightly affects the pressure head fluctuation at the shallower depth. Instead, the simulation of the hydraulic recharge allowed to predict the variation of the piezometric heads at large depth, which are close to the monitored one. So the high piezometric levels at large depth are due to the presence of the deep calcareous aquifer fed in the upstream recharge area, while the fluctuation of the piezometric level are due to the seasonal recharge of the deep aquifer. The stability of the slope has been then evaluated through limit equilibrium analysis performed with reference to a pre-imposed slip surface. The variation with time of the factor of safety normalized to the factor of safety obtained under initial steady state condition is illustrated in this picture. The pattern is characterized by a fluctuation between minimum values in early spring and maximum values in mid-autumn, with a large critical period. In fact, the landslide body becomes unstable at the end of winter and recovers its stability at the beginning of summer, exactly when the piezometric head fluctuations achieve higher values. These results confirm the seasonal nature of the landslide reactivation in agreement with the monitored displacement rates. So to conclude, the numerical study highlighted that the accurate reconstruction of the hydrogeological setup and the appropriate hydromechanical characterization of the slope soils allow a correct prediction of the piezometric regime in the slope and in turn the prediction of realistic seasonal reactivation of landsliding. The Class A uncoupled modeling of the steady state seepage allowed to identify the source of high piezometric heads in the more permeable calcareous layer, representing a deep aquifer. The transient seepage analysis instead revealed that the piezometric head fluctuation observed at the shallower depth are due to water infiltration processes between the top boundary and the atmosphere, while the high piezometric head fluctuation measured at large depth are due to the seasonal groundwater recharge of the deep aquifer. These are some references reported in the presentation, and thank you for your attention.
Thank you so much, Dilernia, for your nice presentation. And I am convinced that you will get many questions at the end of the session. And now it's time for the presentation of Paolo Tommasi. Please, Paolo.
No audio.
L'audio, Paolo, scusa.
Audio.
Okay, it's okay?
Ok.
Do you see correctly the screen?
No.
No. One moment.
Okay, we see your presentation.
Perfect. So, thank you, Mr. Chairman, ladies and gentlemen. I don't know if I will able to answer to the question of Professor Cascini, of Leonardo, but we will give some hints about these topics. When Luciano involved me and other authors in this task, I accepted with enthusiasm because this problem that we will deal in few minutes, in few seconds, our everyday concern or everyday goal for our modeling and interpretation. So these are brief outlines of presentation. We'll speak about structural features of stiff clays and clay soft rocks, because we will deal not only about flysch formations, but also of stiff jointed clay that in many respects are very similar to many structural complex flysch formations. Then we will give some hints about the role of discontinuities in the control of a pore pressure region. And then we will provide some details on 3 case studies: Melfi landslide, Orvieto slide, and Valsebro landslide. And then we will speak about some important, interesting features of the shear zones and in flysch formation with reference to 2 landslides, 2 airflows. And then we will give some conclusive remarks. So according to the classification of Professor Esu in 1977, which was also recalled this morning, we can distinguish two different kinds, 2 different types of I will say clay soft rocks, or structurally complex formation, as you want. The clay types that can be subdivided in 2 types: the layered, the shales and mudstones, the A1, or massive clay shades with massive and shared clay shades, or clays with scaly fabric. This is a term that is very used. It is often used by the structural geologists. This morning, it was recalled in a very interesting presentation about the melange formation, the beam rock formation. And then we have the stiff clays that are out of this panorama, but they can correlate the 2. And then we have the types, some example. This is an example from the very colored clays in Valmaricchia units. These are massive scaly clays. This is a 10 meters long cut, and you can see the structures in the right part that is characterized by a number of shear planes, 1 meter or 50 centimeters to 2 meters long. And then we have also fissures at the specimen scale. We have also joints. I just put the arrow, which are very long, 3-4 meters long joints. So we have 3 kinds of discontinuities at 3 different scales, we can say. This is an example instead from the jointed stiff clay formation. This is the Santa Barbara clay from the Santa Barbara coal mine, and you can see distantly the very regularly spaced subvertical joints, but we have also minor fissures and also horizontal joints in this formation. Then we have the second kind of the second type is represented by the alternation of rocks and clay shale mudstone with fissures, joints, and shears as well. So we can have ordered alternating layers. We can have disarranged mixtures, and we can have completely chaotic mixture of rocks and clay. This is an example of the B3 completely chaotic mix of rocks. This is limestone and scaly clays, and we have an ordered alternation of limestones and shales. So, which is the role of discontinuities? They have a role as a seepage. We can say seepage, but we intend flow through pores and macro fissures. This is a widespread, it's a diffuse flows. But we can have also percolation, that is flow through joints, persistent joints and persistent cracks. We can have, this is the crucial point, is that we can have at the same time the A type of flow, seepage, and the B type of flow. They can coexist and they control both the pore pressure regime. In our experience, we had our monitoring campaigns during engineering works provided very highly complex scenarios that can be understood only if the investigation are detailed and are prolonged over sufficient time to catch the different features of the flow. The numerical models aim to incorporate both processes are welcome. The community, the scientific community, is looking for this kind of integration of large scale and small scale inclusion of flow of discontinuities in the flow modeling. But this is I think is only an open question. We start with the case studies. This is the Murphy landslide in 98 after the excavation of a 10-meter high cut. A landslide reactivated on a very, very gentle slope. The landslide involved a landslide debris, chaotic, with a clay fraction of 20-30% and the plasticity index varying from 45 to 70%. The landslide buoy overlays an alternating regular alternating formation consisting of layers of sandstone and marly clay. The piezometric levels were monitored both with standby piezometers, the yellow one, and Casagrande piezometer, the green one. The red one is a Casagrande piezometer, which will be referred to in the next slide. The cut was stabilized with very complex retaining structures, pile consisting of pile groups, and with drainage shafts with horizontal drains. But in January 1984, the landslide reactivated after a very rainy season. The soil mass was cut into blocks by fissures. You can see the red one. These fissures cut into blocks the landslide body, and the wall was partly overridden by the soil mass and partly was pushed downward and was bended significantly. You can see the plastic hinge in the piles. So though they were not frequent, the piezometer readings suggested that precipitation can cause fast pore pressure increase, followed by rapid drops. This is visible both in the standpipe piezometers, but it's quite visible and more sharply visible in the Casagrande piezometers. And the interesting point is that the sharp increase of pore pressure here in 1986 are correlated with short and intense rainfall events. The highest piezometric values really actually can have been smoothed by the low frequency of reading and also by the piezometer time lag. We are convinced that the many other sharp peak of Casagrande piezometers could be, or a standpipe piezometer could be seen if the readings would be more frequent, and only Casagrande or also piezometric cell would have been used. In 1985, you can see that the water rised over the ground surface. These events were the result of intense but not exceptional precipitation. However, 200 millimeters in 1 month, 1 month and a half. The landslide body was schematized as an assemblage of blocks limited by cracks. Blocks were considered impervious in the short term and subjected to both the pressure in the cracks and both pressure at the base in the shear zone at the base. This was a scheme that was adopted by Henkel in 1967, but also if a simple scheme in the range of residual friction angle measured in on the specimens, the range of the back calculated block length is close to the range of the block lengths that were effectively observed in situ. So this scheme, which consider the development of pore pressure in the fissures without considering undrained condition, but just the cleft pressure in the fissure seems to work in this case. Similar behavior was observed in Valsebre by the group of by the Polytechnical School of in Barcelona, and they observed the same behavior of piezometers, very sharp rise in conjunction with the intense and short-term rainfall, and this was related very well with a very rapid acceleration of the movement. This movement was considered like a stick slip movement, but the stick slip style was probably due to the action of pressure in persistent cracks and joints that were intercepted by the piezometers. Actually, you can see. In Orvieto, we have a very interesting situation. This is a translational this is a translational slide, superimposed translational slides, and the structure of the stiff clays is very interesting because we have jointed softened clays, which is overlaid by debris, a landslide debris, which is formed by remolded clay. Well, both the softened clay, which is not a landslide debris, is in situ, is intact in the same way, is crossed by very persistent vertical joints, but also the overlying debris is cut by very persistent cracks and also by widespread fissures randomly oriented in some way. In this case, we had the vibrating wire cell, so piezometer cell with very short response, very small short time lag, and we see that in jointed clay we have an immediate response to the weekly rainfall. You can see that always when weekly rainfall are sharp, you have a response, an immediate response of the jointed clay. In the clay below, in the non-jointed clay at depth, you can see that the response is delayed. That is, when once the pressure is raised in the joints, then very slowly the pressure rise also in the clay, forming the block between joints. Just to say that we attempted to make transient flow analysis to reproduce the pressure, pore pressure, and we were a little bit successful, we can this analysis rebate the measured pore pressure only if we increase the permeability and we include an effect of the permeability of joints and cracks. Also, if this introduction is not so always correct, because we have also modeled pressure that are higher than the actual one, the measured one. We finished this view just discussing about the increase in hydraulic conductivity, which is observed in the shear zone of fissure formation. Here we have in the Costa della Gaveta earth flow, which develops in fissure formation, and we can see that in the shear zone we have very higher permeability. This is the specific discharge in pumping test. In the shear zone of the earth flow, the pore pressure are quite higher than in the landslide body and then in the underlying parent formation. We can have also 3 order or 4 order of magnitude of difference between the shear zone and the parent formation in the landslide body. This can be considered an effect of the discontinuities that develop in the shear zone and so increase the hydraulic conductivity of the of this zone with respect to the landslide body and the underlying parent formation. Obviously, these values are much higher than those determined from laboratory tests. Same conditions are observed in the Masseria Marino earth flow. First, the full permeability is higher than the permeability measured in the laboratory, because the field test include always the discontinuities in the measure, and the discontinuity that we think about are macro fissures or cracks. And the other interesting thing is that in the alimentation zone here, the permeability is always higher than in the rest of the landslide and in the parent formation. This because this fact can be explained because in the alimentation zone we have a relaxation, so we have opening on cracks, and cracks increase permeability of the whole soil mass. So we can arrive at some conclusive remarks. And in fish formation and the jointed clays, we have both specimen scale and outcrop scale discontinuities that can be responsible of an unexpected pore pressure regime, with sharp difference between the short and the medium long term. The coexistence of more persistent joints and cracks that are connected to the ground surface, this is a very important point, represent preferential path for the rainfall water. This fact, linked with the higher permeability of the basal shear zone, result in a very particular pore pressure regime. In the short term, we have higher pore pressures that act on blocks of the landslide body. And we have also high pore pressure that can establish at the landslide bottom in the shear zone. Conversely, in the long term, we have high pore pressure that rise also in the landslide mass and in the blocks between the cracks. The modeling should incorporate both continuous and discontinuous approaches of the soil and rock mechanics. one of the two approaches could be privileged depending on the structural and geotechnical situation, the problem scale, and the purpose of the analysis. This data, this available data, show that efforts are requested to develop a very special pore pressure monitoring and in situ permeability testing, because both the pressure at small scale and pressure at large scale have to be measured with different devices, and this is to be coupled with better structural characterization of the soil and the part of rock mass at both at medium and large scale. Obviously, we need conceptual models that include numerical analysis that have to account both of the fissured soil mass and both of the large cracks, persistent cracks, and small scale permeability, and of changing boundary hydraulic condition, as the previous presentation underlined. Thank you very much for your attention.
Thank you so much, Paolo Tommasi. I believe that you gave many answers to your question, and I am sure that you too will receive many questions from the audience during the discussion session.
Thank you
and
very
now
much.
is the time to deliver the third presentation of this session. And please, De Rosa, deliver your presentation.
Okay, good afternoon. I will present the paper on the transition of the slides in tectonized clay shales into rapid earth flows, which is a topic much analyzed by Professor Picarelli. And in particular, I will talk about the influence on the transition of the mechanical deterioration caused by infiltration of fresh water. Tectonized clay shales outcrop all along the Italian Apennines. They are affected by several types of instability processes, among which earth flows are widespread and well known for the complex and long processes controlling their evolution. Tectonized clay shales are generally hard materials consisting in weakly bonded aggregates of shear lenses called scales. The soil mass is generally crossed by further major shear surfaces. In the earth flows body, the material is different from that of the parent formation. It is constituted by a softened mass, including lapidus blocks or fragments, according to the scheme of metric supported fabric. The water content of the softened soil is generally much higher than that of the parent formation, and its strength is much lower. Among the different causes of such mechanical deterioration, we think that the chemical changes in the pore fluid composition induced by exposure to rain or to fresh water of confining aquifers plays an important role. To show the effects of exposure to rain, I will present the results relative to the Costa della Gaeta slope and of other two sites of the southern Apennines, Bisaccia and Masseria Marino. The plasticity and the activity of their subsoils vary in a wide range due to different grain size distribution, mineral and pore fluid composition. Anyway, all of them undergo important mechanical deterioration as an effect of natural changes in pore fluid composition. The Costa della Gaeta earth flow develops in a tectonized clay shales called varicolored clays. The pore fluid is a composite ion solution in which sodium is the prevailing cation. The concentration of calcium and potassium are much lower. In the edge zone of the landslide, the sodium concentration is almost uniform in the landslide material and much lower than that in the stable formation. In the main track, it gradually decreases from the stable formation towards the ground surface. It is worth noting that the decrease in the concentration of the pore fluid is not only due to dilution caused by absorption of fresh water and increase in the water content, but also to transport phenomena. As shown by the comparison among the profiles of water content and sodium concentration in the pore fluid, the Bisaccia and Marino clay shales, similarly to the Costa della Gaeta soil, show high gradients in water content and in sodium concentration in the uppermost 5 meters within the earth flows bodies. Let's analyze briefly the effects of the decrease in pore solution concentration on liquid limit, volume change behavior, shear strength, and shear creep. If the limit liquid evaluated with distilled water is higher than about 70%, the Costa della Gaeta soil exhibits a large decrease in liquid limit with an MSL solution concentration increasing, similarly to the Bisaccia clay. A smaller influence is observed for the Marino clay. In all the considered subsoils, the natural water content is always much lower than the liquid limit. To evaluate the effects of exposure to rain of marine origin soils, it's interesting to evaluate what happens when a specimen reconstituted with a concentrate source solution is put in contact with distilled water. The effects are here shown for a specimen reconstituted with 1 molar NaCl solution. The specimen was loaded and then unloaded while submerged in the same solution. In the conditions represented by point B prime, it was exposed to distilled water. The exposure caused large swelling. Since swelling occurs under constant Terzaghi's effective stresses, it is represented by a straight line normal to the abscissa. In the considered case, it can be observed that swelling is almost such to bring the overconsolidated material close to normal consolidation conditions. The swelling curves against time show that such osmotic swelling is very slow and is much slower than the mechanical swelling. In the case of the Bisaccia clay, the osmotic swelling caused by exposure to distilled water is much higher than that of the Costa della Gaeta, and the chemically induced swelling curves intersect the compression curves obtained with source solution and go towards conditions possible only with distilled water. Analogous behavior is exhibited by the undisturbed material. Thus, exposure of overconsolidated clays of marine origin to distilled water can induce swelling that can turn the strongly overconsolidated soil in a soft soil with contractive behavior. This softened soil, as an effect of undrained loading, can thus experience pore water pressure increase. When such phenomena occur, for instance in the alimentation zone of the landslide, it can cause a flowing mechanism of movement. This type of mechanism is characterized by the displacement profile of a fluid, different from that of a solid sliding mass. The different mechanism is shown in this figure for the case of the Miscano Valley earth flow. The volume change behavior of undisturbed specimens is not always influenced by the pore fluid composition, as shown by these figures, which report the odometer curves of couples of undisturbed specimens of the 3 soils. One specimen of the couple was submerged in distilled water, and the other one in 1 molar NaCl solution. The figures show that the contact with distilled water leads to large swelling, much larger than that observed while in contact with the concentrated source solution for the Bisaccia and Marino clay shales. The influence of pore fluid composition is negligible for the considered soil of the Costa della Gaeta clay shale. Even so, however, pore fluid composition influences the shear strength parameters. The influence of pore fluid composition on the peak shear strength of normally consolidated specimens is here shown for Bisaccia and Costa della Gaeta soils, characterized by the initial conditions represented in the upper figures in terms of void ratio. In the case of the Bisaccia clay, the decrease in strength with pore solution concentration is associated to the higher void ratio of the water-saturated specimens. In contrast, the analogous decrease in strength for the Costello Agaveta soil occurs without volume changes. Analogous effects of pore solution concentration can be observed on the residual shear strength. The results show that the residual friction angle decreases from a maximum of 14 to a minimum of 6 degrees, in some cases even 5, with the pore solution concentration decreasing. To simulate the effects of the decrease in pore solution concentration in the field conditions, we also carried out direct shear tests under constant shear stresses, that is, creep tests. In particular, some specimens were prepared by mixing the powdered material with 1 molar NaCl solution, were immersed in the same solution and sheared at a constant displacement rate until the residual state was attained. Then the specimens were submitted to shear stress lower than the residual strength in source solution, but higher than the residual strength in distilled water. The effects of such stresses on shear displacements were negligible. Then the cell solution was replaced by distilled water, renewed frequently to remove the ions diffusing from the specimen into the cell water. As a consequence of this exposure, the displacement rate increased with a non-linear trend, as in a tertiary creep stage, while the residual strength decreased. Summing up, the natural pore fluid of tectonized clay shales of the Italian Apennines is a composite ion solution whose concentration varies greatly with depth from the ground. The decrease in ion concentration with respect to the initial marine condition is the effect of several natural transport phenomena and absorption of fresh water. The natural decrease in pore solution concentration can cause large swelling and softening in active clays and causes anyway a decrease in the strength parameters in all types of clays. Swelling and softening can be such that any cause of undrained loading, for instance, alimentation from the main or from the secondary scarps, differential movements within the landslide body, can induce positive excess for water pressures in the mass, which can thus start flowing. Thank you for your attention.
Thank you so much, De Rosa, for your nice presentation. And now is the session time for discussion. So, Marinos, the microphone is yours.
Okay, now we start with the discussion. I will remember you that if it's possible to say some question with the Professor Pinol that has already discussed yearly.
Okay, so can you hear me? Can you listen to me right now?
Yeah.
Okay. Also from my side, I'm very happy being a convener in this conference. Very sorry that we didn't have the opportunity to be hosted by you. This is a terrific opportunity for these regional discussions of landslides in these formations we all have. And, we saw a perfect example of how in specific triggering factors can be analyzed. So in this case, as you all saw, and you can read from the full papers also, we see very good examples of case studies and analysis One from hydrogeological aspects mainly, and how this hydrogeological setup and these piezometric fluctuations can be analyzed in detail, and also connected with the hydraulic conductivity. We will see about the climatic variables. We will discuss about that, how this can lead to failure, and how this can analyze numerical analysis. And the second one was very nicely focused on the structural features of our material. We call it fleece, we call it clay. Maybe clay can derive from fleece, as the last cases, textonite scales. But it was the authors try to, let's say, try to model, try to back analyze how these failures derived, and how these pore pressures could be induced within the rock, within this sheared mass, and how this can vary also in the landslide body, in the basal surface, and below in the parent rock. And they try to read these very rapid fluctuations, induced pore pressures through the piezometers, and also some old works of bodies, let's say, specific blocks within this landslide body, and how the hydraulic conductivity can be larger than we thought it would be from some initial tests. And the third one was a very nice work about, let's say, chemically induced softening, and how the material can be deteriorated in time. Of course, this work was focused in more shallow slides, and how a landslide body can, let's say, shift to a flow, a mud flow, an earth flow, and how the chemical changes and how the water, the pore solution concentration can influence this material deterioration, and the shear strength reduce through the opening of the rock mass, through the increase of void ratio. And also this work was very, very nicely presented. All the three works, though they all came from the Italian peninsula. However, the Italian colleagues have very good experience into that, and they have very good data from the past into that. So these were terrific opportunities for them to try to analyze that. I don't know if we have, if I can see the questions of the participants, and we can guide that, or I can just start with some discussion into that, or maybe we can bring the participants within the discussion also. Can you please guide me into that?
Yes, Professor Marinos, you could start with the discussion.
Yeah.
We have
so are there any questions? I don't see any. Can't you?
So we have no question at the moment.
Okay. Please, I will start some discussion, but if we have a lot of participants, so please pose your questions, and we can make some discussion into that from your experience. So I would like to make some discussion with the first presentation presented by Dilernia about the how the some climatic variables can cause very low, let's say, factor of safeties. We show very good of how these piezometric fluctuations can change the factor of safety. But I would like to ask a little bit to be more certain about these climatic variables. So when the authors say climatic variables, they speak mainly for, let's say, the change in the piezometric level due to the change of months of let's say the winter and the summer periods, or there is something more to that through the evaporation, through the vegetation, because there is some notes about the vegetation and all this, let's say, interaction.
Okay. The net rainfall has been evaluated taking into account the daily total rainfall and the evapotranspiration flux that was determined adopting the dual crop coefficient approach of the Faupe-Montit method. So observing in situ that there is the vegetation of winter wet, we selected a thermopluviometric here that was in this case 2030 and 2014. And then we evaluated using the thermopluviometric here in this with reference to this year and the vegetation of winter wheat, we evaluated the coefficient, the basal crop coefficient, and the soil evaporation coefficient, assuming a percentage of cover in the slope. So basically, the evapotranspiration flux has been determined through the dual crop coefficient according to the Faupe-Montit method.
Okay, thank you very much. So I would also like to discuss about let's back analyze. We saw how important it is to try and back analyze all these landslides we have and try to find the pore water pressures at the time of the failure. However, there are cases when I will mostly go now to the second paper presented about how they if you back analyze, let's say the landslide, the first example, the large landslide, and with all these very high piezometric level above the surface, and also having some good, let's say, appreciation of the shear strength, cohesion, and maybe zero, and friction angle very low. Again, the factor of safety, let's say, it was not, let's say, close to what we expected. So you tried to put that into, let's say, more progressive failure, or to try to put these discontinuities into your analysis and say that we had some large vertical cracks, probably due to the relaxation of these old movements. So you had certain areas along the sliding body where you had these open cracks, and maybe in some cases these were wider and these were smaller, but you had some, let's say, persistent wide cracks. That's why you had these very high pore water pressures in this case. So I understand that the water could easily go within the landslide body and go below at, let's say, the shear surface. what I did not very well appreciate, very well understood, and I wanted to discuss it with you, was why we had this larger permeability, this larger hydraulic conductivity along the basal surface, and not also to the landslide body, because through these open cracks, of course, maybe you said a more homogeneous conductivity of the landslide body. But yet again, we had these open fissures in the landslide body, and the water could easily reach in depth. And that's why we had this deep sliding. Otherwise, with this cohesion and with, let's say, the pore pressures you measure from the permeability values before, in no way you would have in your analysis, in your numerical analysis, this kind of sliding in depth. So somehow you had very large pore pressures in depth through these blocks opening and these blocks, let's say, separation. So the landslide body also would have this larger permeability. But yet again, you said that the landslide body had the less permeability than the basal shear surface. Of course, the parent material, we understand the lower permeabilities. And you made very nice comparisons of the values measured in situ and from pumping wells. So this is one question I have to discuss.
Okay. May I answer?
Sure.
Well, the cases that we shown were analyzed by 3 different research groups. I can answer for what we did in Orvieto, but I think that I can also interpret what my colleagues think, and if they have different views, I invite them to answer to you as well. So for Orvieto, we have a problem that I think also in Melfi and probably also in Costa della Capita or in Masseria Marino is that when you install piezometers, many of the in situ field measurement of permeability are conducted, I think all, with the exception of Costa della Capita, all measurements are conducted with falling head tests in Casagrande piezometers. That's okay. So when we carried out borehole cores, and we examined carefully all the cores of the boreholes, we didn't find any joint in cores. So the piezometers were installed in the boreholes, and so piezometers didn't intercept any joint. Mm-hmm. So this is interesting because when you put the piezometers, if you make only measurements with piezometers, with Casagrande piezometers, you have an intake zones which usually is not long. I think it can be 60 or 80 centimeters, not more. And probably it could be absurd, because we always say that in clay soils we have not to use standpipe piezometers, but perhaps in some cases standpipe piezometers can give you more interesting information for the fluctuation of the piezometric levels, because they intercept joints and cracks. So one of the reason is this, that for this reason I told before that we have to think better about what kind of test we perform. Probably the test that were performed in Costa della Capita, pumping test, could be more interesting, but they have the same problem. For example, I have a lot of experience with Lujon tests in rocks. If you have vertical joints, Lujon tests are not effective, for example, even dams many times. So it's very difficult to include the effect of joints, vertical joints and vertical cracks in the permeability field testing. This is what I can say. You should make, for example, pit test. It could be more and more interesting.
Definitely, when you know, let's say, better the geological conditions and when you expect these fissures and if they are intersecting or not, then you know, let's say, all the limitations, and you can interpret these results. You can take them in analysis or not, and you say, I don't trust them. Somehow, of course, you need to make them. And as you noted, and I saw also the other authors did in their papers, the laboratory tests in these cases do not help because they have this, they are very, very small scale. So yes, you cannot catch this permeability that it is induced in this kind of environment.
Right.
Of course, you will get very, very low values of permeability. So what you discuss is quite clear. And
can I add just a comment, and that's all? Well, when we modeled the landslide, the transient flow in the jointed clay, we didn't use permeability values from tests, but we were lucky because we had cut. You saw in the pictures, we had cut. So we have 10-15 meters of clay exposed in cuts. So we made a very careful survey, spacing survey of discontinuities, and we derived theoretically permeability, the permeability tensor from the spacing survey of discontinuities.
Yeah, thank you very much. And you discussed the necessity of this medium scale and large scale permeability testing, which is also very important. So we don't have only the percolation issues, we have also this seepage within the fabric of the material. So we have to try to analyze both groundwater presence through this different kinds of hydrogeological assessment within this very complex material we're working on. So I would expect that this compressed area in let's say in the shear surface, when you have this shearing, this basal area would be a little bit lower as permeability, and all the above, let's say, material would have this highly heterogeneous, of course, permeability, not homogeneous, through these vertical joints you discussed. And so this is something that you did it with your open pit, and you try to analyze it, and you understood the hydrogeological issues and how the water can percolate into that mass. And going through the third paper presented by De Rosa, sorry, by the paper of Picarelli et al., we saw a very nice analysis in chemical influence softening and many comparisons about the sodium concentration and the fresh water and the post-solution concentration. So I think this is something that we must work before. I don't have any particular question very much into that. My only question would be here, in what kind of depth, let's say, you would appreciate that we could have this chemically influenced softening, so we can have this shifting from the sliding to flowing masses. What is your appreciation based on your experience until what depth we could have this pore solution concentration and large swelling and softening in these active clays.
Yes, in the stable formation, 3 or 4 meters. Instead, in landslide body, for all the body of the landslide.
Yeah. So you would believe in your case it was like 3-4 meters.
Sorry?
So you think this can go even more than 3-4 meters in these tectonized shell clays?
Yes.
Even more within the whole sliding body, you said?
Yes, yes, yes.
Okay, so I understood that this softening is made easier because you had this more relaxation, your rock is more open, and the fissures are more open. So this swelling and softening can be easily done. Maybe after some meters, this tectonic shale clays have a more close structure, or you think due to their tectonized nature, this can be also transmitted, and this process, the deterioration process, can go 10, 15, 20 meters also?
Yes, sure. Swelling depends also on the axial shear stress. Yes,
Okay,
the vertical
sure.
shear.
Yeah. Okay. So this, if there are no any other questions by the participants, I would say this all these 3 examples, these very nice presented case studies, and I would take the opportunity to say that we need the case studies and some publications now, journal papers. We need to make many equations in order to be published and to be based in something new prototype, but we need this experience to be published, especially in this complex material. It's a case study, but it has a lot of valuable data by experienced people. So if these are correlated with some testing, in situ testing, and some analysis, I think there are perfect examples of how these case studies can be highly, very valuable to everybody. So thank you very much for giving these case studies and analysis. And thank you very much for also inviting me, being convener in this session.
Thank you very much. And now we finished this. If you have any question, somebody.
I think that there are no other questions, so Professor Cascini can close this session.
Thank you so much, Luca. It has been a pleasure to be the chairman of this session. 3 very nice presentations. Many questions from Marinos in order to explain some aspect of the presentation. And so once again, thank you to all the speakers and Professor Marinos. And thank you so much to invite me as the chairman of the session.
Perfect. Now this is starting the break, so we have to see at 4:10 just for the next session mechanisms. See you later.